Our modern world relies on a hidden translation process, taking raw, spinning mechanical force and converting it into electrical current. We owe the blueprint for this conversion to Michael Faraday. He discovered that if you physically move a copper conductor up and down through an invisible magnetic field, it induces an electromotive force, or EMF, creating a live current. Pushing a wire through magnets is the simple mechanical foundation of all electrical generation. But this physical reality comes with a counterintuitive catch. This diagram shows a cross-section of a wire loop rotating continuously inside fixed north and south magnetic poles. Because it spins in a circle, the physical direction of the wire relative to those poles flips every half turn. Therefore, the flow of the electrical current generated inside that wire naturally reverses back and forth right along with it. This rotational reality ensures that every generator, even one designed for DC output, is actually producing alternating current inside its core. If the laws of physics dictate that a spinning coil must make AC, how is a DC generator that outputs a stable one-way current even possible? Before engineers can fix that alternating current, they have to predict exactly which way it is flowing. That brings us to John Ambrose Fleming. He designed a mnemonic known as the right-hand rule to predict current direction in generators. Look at this diagram showing the thumb, index, and middle fingers extended at strict 90-degree angles. The thumb maps to the mechanical thrust, or force. The index finger maps to the direction of the magnetic field. That leaves the middle finger to point directly to the resulting electrical current. This rule proves that the electrical current's direction isn't random. It is entirely locked to the physical motion of the conductor. By knowing exactly when and where the current will reverse, engineers gained the precise blueprint they needed to physically hack the system. This diagram reveals the solution, the commutator, or split ring. The timing is exact. Just as the internal AC wave is about to reverse, the split ring rotates past its gap. As a result, the outside connection flips at the exact millisecond the current reverses. The alternating current is still happening inside the armature, but the commutator acts as a real-time mechanical translator. This mechanical trick forces the output to flow in one single, uninterrupted direction, direct current. The DC generator is essentially a standard AC generator equipped with a brilliant mechanical filter to trick the output. Manipulating these laws comes with side effects. The inside of the generator turns into a battlefield of opposing forces. This visual illustrates the first major conflict, armature reaction. As the armature generates current, it spawns its own rogue magnetic field. This secondary flux actively fights against and weakens the main magnetic field that created it, dragging down the machine's efficiency. The second opposing force is voltage drop. Think of it like pumping water through a very long pipe. The sheer distance and friction cause you to lose pressure along the way. The armature's own internal electrical resistance acts like that long pipe, stealing some of the generated voltage before it can ever leave the machine. Generators are locked in a constant state of fighting their own physical byproducts, forcing engineers to add hardware like compensating windings just to keep the machine from defeating itself. We can see the DC generator as a sophisticated engine of translation. It functions as a high-stakes arena where raw mechanical motion is wrestled into electromagnetic induction. The internal alternating current is mechanically wrestled into DC via the commutator, while compensating systems fight off internal resistance and rogue magnetic fields. Harnessing electricity requires outsmarting the laws of physics at a microscopic level to provide the steady power that runs the modern world.